Hello everyone, in this video we will discuss about internal 1 part B. This video is based on similarity and dissimilarity measures. This video consists of detailed answers to questions on nominal, binary and vector and ranking questions. Question number 5. Briefly outline how to compute dissimilarity between students' feedback profiles described by nominal attributes, asymmetric binary attributes, numeric attributes, term frequency vectors. First, nominal attributes. Nominal values are categorized without order. For example, department, CS, EE, and ME. Common approaches. First is simple matching. Binary similarity, that is also called binary similarity, for two profiles P and Q for a nominal attribute. Now, as here is similarity, similarity of P and Q equals to 1 if same category and 0 if different category. Dissimilarity D equals to 1 minus S. For multi-attribute nominal vectors, average or sum the mismatches. Now, one hot encoding plus numeric distance. Convert each category to a binary vector, one hot, then use like example cosine or Euclidean on those binary vectors. This allows mixing with other attributes types. Now third here we have overlap coefficient or matching coefficient for multi-valued nominal attributes. If an attribute may have multiple choices, example electives chosen, use overlap or J card. Uh, J of A and B equals to A intersection B, mode of A intersection B divided by union of mode of union of A and B. Dissimilarity equals to 1 minus J. Now B, asymmetric binary attributes. Asymmetric binary means one is presence or is more informative than zero absence. Example, attended workshop yes or no, where yes matters more. Common metric J card coefficient. For in this we will ignore 0 matches. For two binary vectors PQ, J of P and Q equals to M11 divided by M01, M10 and M11. These are where M11 is number of attributes both have 1. M10 means attributes P equals to 1 and Q equals to 0, and M01 equals to where and M0 is where P equals to 0 and Q equals to 1. Dissimilarity equals to 1 minus J. Now numeric attributes for CGPA and attendance percent. Numeric attributes support mainly classical distances measure. For distances measure, we have here Euclidean, Manhattan, Chebyshev distance, standardization or scaling, and Mahalanobis distance. Numeric attributes. Numeric attributes support many classical distance measures. Euclidean distance. Here dE of x and y equals to under root of all the xi minus yi whole square. Manhattan L1 distance. Here d1 of xy equals to sum of all modulus of xi minus yi. Chebyshev distance, maximum absolute coordinate difference. Standardization and scaling. Before computing distances, standardize z-score or scale to 0 to 1. Otherwise, attributes with larger range dominates. Here, zi equals to xi minus mu divided by sigma. Mahalanobis distance accounts for correlations dm of xy equals to under root of x minus y to the power t and s inverse into x minus y, where s is covariance matrix. D. Term frequency vectors. Keywords in open text feedback. Text is typically represented as vectors. Term frequency TF or TF-IDF. Common similarity measures. First, cosine similarity. Measures angle, ignores document length. Cos theta equals to modulus of x into modulus of y divided by x dot y. Dissimilarity can be 1 minus cos. Euclidean on TF or IDF normalized vectors. Compute TF IDF then normalize. Euclidean distance between normalized TF IDF vectors relate to cosine. KL divergence or Jensen-Shannon for probability distribution. Treat normalized TF as probability distribution requires smoothing. Soft measures or word embeddings. For semantic similarity, use average word vectors or sentence embeddings and then cosine. Question number 6. Suppose two student-faculty interaction profiles are represented as tuples. P equals to 22, 1, 42 and 10. Here it is a comma. And Q equals to 20, 0, 36 and 8. Attribute represent hours mentoring, projects review attended and assignment submitted, infrastructure usage count. Compute. We have to compute Euclidean distance, Manhattan distance, Minkowski distance with h equals to 3 given. Supremum distance. Step 1. Compute coordinate wise differences. Here P minus Q. 22 minus 20, 1 minus 0, 42 minus 36 and 10 minus 8. This gives us with tuple 2, 1, 6 and 2. Let the absolute differences be modulus of all these values. And now Euclidean distance. By applying the formula of Euclidean distance, we got the value 6.7082 and so on. Now, now Manhattan distance. By applying the formula for Manhattan distance, we get 11. Now Minkowski with h equals to 3 given. By applying the formula, we get here 6.15344. And supremum distance is max of all the values, so here we have 6. Question number 7. The median score is often a key holistic indicator when dealing with massive student feedback datasets. Propose methods for median approximation, analyze their complexity and suggest heuristic to balance accuracy versus efficiency. Now exact methods when feasible. Deterministic linear time selection, median of medians, worst case on time, O1 extra space. Good when you need exact median and can read data multiple times or have random access. Streaming or large scale approximate algorithms. First, two heaps. Running median, maintain a max heap for lower half and a mean heap for upper half. Each new element inserted in O log n time, median retrieved in O1. Memory On if you keep all elements, but if streaming and you must keep n. Memory grows. Practical for online median if you can store data. Reservoir sampling plus exact median on sample. Keep sample of size k, example k equals to 10 to the power 4. After the stream ends, compute median of sample exactly. Time on to sample, o k log k to sort sample. Error can be bounded possibility with large enough k you get. Tight confidence intervals. Good heuristic when you can tolerate probabilistic error. Approximate quantile algorithms guaranteed error. Greenwald-Khanna GK algorithm. Deterministic provides E approximate quantiles with space, stream friendly, D Q digest and T digest practical measurable and T digest is excellent for extreme quantiles and distributions, small memory and good accuracy for median. Complexity update cost typically or am- amortized constant. Complexity update cost typically or amortized constant. Memory is 0 1 E. Histogram binding approach. Maintain fixed beans counts, approximate median by walking cumulative counts, space equals to normal number of beans B, accuracy depends on bin width, fast updates O1, good for bounded range data. Distributed map reduce approach. Compute local summaries quantile sketches on partitions and merge. Mergeable algorithms like GK or t-test are preferred. Complexity, linear total work across nodes, low network overhead to send digest objects. Now here we have difference between accuracy heuristics and efficiency heuristics. Goal, produce the most accurate or optimal solution, and goal of efficiency heuristic, produce a fast and acceptable solution. Computation time for accuracy, high slower algorithms. Computation time for efficiency, low and fast execution. Resource usage, for accuracy, high CPU, more memory, and efficiency heuristic, low resource consumption. Solution quality of accuracy, optimal or near optimal, and solution quality for efficiency, approximate or good enough. Search method for accuracy, exhaustive or highly informative, and search method for efficiency, limited exploration and shortcuts. Risk of error, very low in accuracy and higher possibility of error in efficiency. Use cases, scientific computing, medical systems, optimal planning, and etc. Use cases for efficiency heuristics, real-time systems, navigation, games, large AI searches, and etc. Examples of accuracy heuristic, a full dynamic programming, optimal planning, and examples of efficiency heuristics, greedy best first search, and hill climbing beam search. Scalability, poor for very large data, very high scalability in efficiency. Or where to use, when accuracy is critical and efficiency when speed or efficiency is more important. Now question number 8. Given the sample dataset, two attributes, faculty responses A1 and infrastructure support A2. Table of students S1 to S5. From the sheet, we interpret each student as a 2D vector A1, A2, where rows are attributes A1 first row and A2 second row. The table values are given in this table. Now, feedback query x equals to 1.4 and 1.6. The task we have to perform: first, rank existing students' feedback profiles similarity to similarity to X using Euclidean Manhattan supremum and cosine similarity. Normalize each student's vector to unit length and recompute using Euclidean distance. Common formulas restate. For Euclidean, we have under the root x1 minus y1 whole square plus x2 minus y2 whole square. Now Manhattan, we have d1 of xy and modulus of x1 minus y1 plus modulus of x2 minus y2. For supremum, we have d of xy equals to max of x1 minus y1 and x2 minus y2. For cosine similarity, we have cos theta equals to x dot y upon double modulo of x and double modulo of y, where x dot y equals to x1 y1 plus x2 y2. Higher cosine equals to more similar. Normalization of vector. U norm equals to u upon double modulo of u. We compute each quantity for S1 to S5 versus x 1.4 and 1.6. Step-by-step calculations. Differences for each student component wise. Compute Si minus x. So S1 we got 0.1 and 0.1. For S2 we got 0.6 and 0.3. And for S3 we got 0.2 and 0.2. And as for minus 0.2 and minus 0.1. For an absolute value for this 0.2 and 0.1. Now S5 we got 0.1 and minus 0.6, and absolute value of this are 0.1 and 0.6. Distances or similarities. Euclidean distance d. By solving with formula, we got 0.1414 and so on. And for S2 we got 0.6708 and so on. And for S3 we got 0.2828 and so on. And for S4 we got 0.2236 and so on. And for S5 we got 0.60827 and so on. And here are the Euclidean ranking closest to farthest. First is S1 is very closer than S4, then S3, then S5, and farthest we got S2, which value is 0.6708. Manhattan distances here sum of absolute coordinate differences. Now for S1 we got 0.2 and S2 we got 0.9 and for S3 we got 0.4 and for S4 we got 0.3 and S5 we got 0.7. Here are the Manhattan ranking closest to farthest. First is S1 very closer, S4, then S3, then S5 and we got farthest S2. Now supremum distance, maximum of coordinate absolute differences. For S1 we got 0.1 and for S2 we got 0.6 and for S3 we got 0.2 and for S4 we got 0.2 and S5 0.6. Now ranking S1 S1 and S3 tie and S4 ties with S5 and S2 0.6. Cosine similarity, first compute norms. So norm of x equals to 2.16039 and S1 we got 5 under the root 5.14. By solving further we got 2.266 and so on. We'll use more precise numbers below. Now compute dot product and cosine. Dot product we got 4.82 and norm of x equals to 2.26602. So cosine equals to 0.9991 and for S2 we got cosine equals to 0.995752. Now for S3 by applying the same formula we got 0.999969 and for S4 we got 0.999028 and for S5 we got 0.965363. Now cosine ranking S1 is from higher equals to more similar. So here S1 is higher. So first is S1, then S3, then S4, then S2, then S5. Normalize each vectors to unit length and recompute Euclidean distance. Now first we will normalize query. So x equals to under the root 1.4 square plus 1.6 square by which we got 2.126039. Now by norm for normalizing x we will divide by 1 we will divide 1.4 by 2.126039 and 1.6 by 2.126039. So we will get 0.6585046 and 0.75255767. Now step 2, normalize each SI. So here S1 we got 2.26602 by normalizing 0.6616 and 0.74983997 and S2 we got 0.724994 and 0.6887495. Now similar we got S3 values and S4 and S5 values. Step 3, Euclidean distance between normalized vectors and x norm. Now for this we will use formula D equals to norm of SI minus norm of query. So S1 norm versus X norm, we got distance by applying the formula. We got distance 0.0041495 and similarly for S3, we got 0.0078122 and for S4, we got 0.44085549 and for S2 we got 0.092179091 and for S5 we got 0.26319805. Now ranking after normalization Euclidean on unit vectors. First S1, then S3, then S4, then S2, then S5.